So hi, I'm Julien. I'm the processing tools tech lead for data platform. I'm going to talk about Parquet, a columnar file format for Hadoop. So first, I'm going to give you a little bit of context of why and how we came to start Parquet. And then I'll give you some production numbers to give you an idea of what we got out of it. And then I'll explain more the details of the format. So at Twitter, we have a lot of data. Right? I give you, those are our official numbers from a few months ago. So we have over 200 million monthly active users, and they generate and consume, interact with over 500 million tweets a day. And that generates a lot of data. So often people talk about Twitter scale and they talk about the fire hose, which is a stream of all the tweets. But we actually have a lot of more data than that. So the data is all about the instrumentation of the site, like knowing what you click on, what you interact with, what you search for, if a tweet was displayed or not, if you saw it. And having all this information so that we can measure engagement, try to understand why or why not people are using the site. And that's a lot more data than just the tweets. And so to look at that, we have the analytics infrastructure, and we have several over 1,000 node clusters. And there's a log pipeline that will ingest all that data and make it available 1 hour at a time in 1 hour partitions on Hadoop, so that to simplify this. And so, as we talked about before, the data model we use for all our data is based on Thrift. So Thrift was already used for all the client-server communication. So it's just easy to use those same objects in the same model to log events of what happened. Like if you want to log that a request happened, it's just easy to take the structures that represent that request and log it to a file. So we use Thrift to log what's happening on the servers. And here's an example of one of our data structures. So because those things represent real life things, so Thrift is actually a nested data structures, right? You can have primitive types of structs or lists, maps, and sets, and then can be fairly nested. This one in particular, you can see that you have information like an IP address, a country, a user ID, things describing what happened, and a bunch of other data structures that describe what happened. And this one in particular has 87 columns and up to several levels of nestings. So it's fairly like deeply nested data structure. And that's one of the challenges of storing that data in an efficient way. So the goal of Parquet was from the beginning to have a state-of-the-art columnar format across the Hadoop infrastructure. So it was a very important design goal to be language independent, to be framework independent, and to be really easy to integrate with a bunch of different object models of different frameworks. And I'll talk a little bit about this later. So Hadoop is very reliable, and you can do very large-scale scanning of files. It's also very I/O heavy. And it's not like the most efficient way of scanning that data and using it. And that's something that MPP database, parallel DBs like Vertica or those types of things, I've been using for a long time. Columnar Storage to optimize your I/O and be a little more efficient at doing that. So the goal was to bring some of those technologies into Hadoop and be a little less of a file system and a little more of a database. And so those are the goals of Parquet. Now is the kitten picture that you always have in Hadoop-related projects. So columnar storage, right? Should be obvious now. So the goal is to limit I/O to the data you actually need, right? Because I showed that gnarly data structure, like 87 columns, but really what you want to do is count how many requests I have per country for a given thing, right? So you will want to access 3-4 columns out of those 87. Usually when you query, you really don't need all of the columns. So as you saw in Oscar's presentation, where we're doing this transformation, And the idea is, instead of reading the first value of the first rows, skipping to the next row, reading the second value for the same column, and so on and so forth, and just seeking. Instead, because we organize the data column-wise, now we can scan those columns efficiently, and all those spinning disks are optimized for, like, they're much more efficient at scanning data rather than they are doing like a lot of small seeks and small jumps on the data. So that's one aspect, right? To have more efficient scan, reading only the data that you need instead of having to read everything or doing a lot of tiny seeks. Yeah. So the question is, does that mean that compression context is reset for each column? Yes. So as we said, each column is compressed independently, right? So now, because we organize things per column, like Oscar talked about this in his talk as well, it's going to be compressed per column. So now, yes, when you scan, you want to decompress only the columns that you need. So it's compressed per column for that, and it's going to compress better because now the data in the same column is homogeneous. So it compresses better, and also we can take advantage of, now it's always the same type in that same column, right? It's always an int, or it's always a string, because those columns are typed. So you can also have more efficient encodings to source those values. In particular, integers, and I'll talk about that, so maybe I'll just go quickly on that. Instead of having to always use 4 bytes, you can combine all those ints together and use a lot less, especially if you know that the maximum int is like 4. Now you can use 3 bits to store each int and do much more efficacious. So it improves I/O and it improves storage footprint. So we started this project initially as a collaboration with Cloudera. So we both had a prototype of building a columnar file format. And at some point, we just, I talked a little bit on Twitter, and I got contacted by people at Cloudera, and we talked about it, and we decided to merge our efforts. And one of the great particularity of working together on that is that Impala is written in C++, and so that gave us very strong enforcement of language independence, right? So the format is formally specified because we have 2 implementations of reading and writing it, one in Java and one in C++. And it gives you an important need of looking at things like using little engines for ints, for example, so that because Impala, which is written in C++, will worry about being able to cast automatically a byte array into an int array and have much more efficient access to it. So here are some numbers. And so what we took one of the big log categories that we have, that is basically one entry for each HTTP request on the front end. And it has 30 columns, and you have things like the IP address it's coming from, the machine server name, when it happened, the user ID, all those things in different columns. And originally, it was Thrift binary format in block compressed files. So we use LZO for compression because algorithms like LZO or Snappy are much more CPU efficient. So they're good trade-offs. They compress a little less than gzip, but they're much more CPU efficient. So you don't trade off that much CPU for the space and the I/O you gain. And we're converting them to Parquet and still using LZO. So instead of compressing a whole block, LZO will compress by block, and compressing all the columns together per rows, we're compressing one column at a time, right? So it's compressing per column. And just doing that, we gain 30% in space. So instead of storing it by row, we store it by column, and now it compresses much better, right? So we save 1/3 of the space. And scan-wise, so I kind of gave 2 extremes here. If you scan only one column out of those 30, it takes 10% of the time to scan just that because you scan a lot less data and it's a lot more efficient. In the other case, you were scanning everything, but just keeping only one column out of it. And in the case where you scan all the 30 columns, which is a worst case scenario, here we're seeing an overhead of 10% in time, which is reasonable trade-off. And the reason is because now that we split things in columns, to pass it to pig, so that's using pig, you need to reassemble those columns. So there's the overhead of reassembling those records. And I think that's something that I hope we can improve as well, because we are also loading less data. So we should be able to, by improving performance of this assembly algorithm, probably offset that a little bit, because we're gaining on I/O a lot, right? It's 30% smaller than the original data set. So that's what we're seeing on those logs, the results of the performance improvements. And I gave here some other examples. So you can't really, it's not a benchmark, it's actually production numbers. So the advantage of a benchmark is you can reproduce on something else, so you can compare things. The inconvenience of a benchmark is that it's not very representative of production workloads. Here we're doing it on our production workload. The problem is I'm not going to tell you what this job is doing or what the data is. So it's kind of, but it's like real life things. So we took 2 jobs, and one of them is in pig, the other is in Scalding. And it's not saying that it improves better Scalding that it improves pig. Those jobs are doing different things, so you can't really compare them. But just some examples. So depending on what the job is doing, what columns it accesses, and whether it's reducing a lot of the data we read or not, we can see gains in how long it takes to scan that data. So here are some numbers. So on pig, we're reading 32% less data. So we're loading most of the data, right? 70% of the data we loaded still, and we're seeing a 20% decrease in time it takes. And the Scalding job, we're reading 80% less data, and we have a 60% time saving. So you can see that it's not proportional to how much less data you're reading, but it's still in the same ballpark. So, and those jobs run every hour, right? Every hour we add a new partition, we do a new report on it, and we export to a dashboard to simplify. And so that's like terabytes of scans saved every day from reducing that. So that's resources that can be reused by some other jobs. So now I'm going to talk a little bit about the format. And in particular, I'm going to explain how we turn those nested data structure into flat things that fit into columns. So the format is columnar, but it's columnar per row group, right? So when we write into columns, we need, the records come one at a time, right? So they come in a row format, one row at a time. And we need to turn it into columns, which means before we can write one column in the file and then the second column, we need the first column to be fully encoded in memory, right? So we need to buffer all that data in memory, one row group at a time, to store it in columnar format. And so we split the data in row groups, and each row group is in columnar format. So the row group would be roughly something like around less than 1 gig. That's how much data at a time you would have in columnar format, and that enables much more efficient scans on each of those columns. And so a column chunk is how we call the chunk of the column inside a row group. And then each column chunk is split into pages. And the page is the unit of compression, right? That's a granularity at which you can read, like let's say you would want to read a single value, you would have to decompress a page that contains a certain number of values and get to it. So a page would be like something like 64K, and that's a unit of compression. So if it's a page is too small, it's not going to compress as well. And if it's too big, you increase the granularity at which you can access the data. And so the file is, in the file you will have row groups one after the other, like I show in this diagram. Each row group has each column one after the other. And at the end of the file, there's a footer containing the metadata. In the metadata, you have things like the schema of the file, and all the pointers to all those column chunks, so that when you read only a subset of the columns, you can actually read only those columns and efficiently scan through them, right? So when you access the data, it's going to generate splits based on the information in the footer. So each file is self-contained. It's containing its own schema and the metadata to read it efficiently, which is useful because now, like in things like Pig or other languages, the file is self-contained and contains in metadata, so you can easily move it around and still look at it without having to know what the schema is. So I explained how our data structures are deeply nested, like, and you have list and repetition and nested fields. And then I explained how we just store them flat in columns. So there's a missing piece here. And what we did is we used the algorithm described in the Dremel paper. So Google published this paper, I think, 4 years ago now, and described how to store nested data structures into columns using something they call repetition level and definition level. So for each value, you will add a little bit of information called the repetition level and the definition level, and they are a generalization of how you would store null. So if you imagine a flat schema, for each column, you could use a bit to record whether the value is null or not, assuming things are nullable. You would store the value, and you could use a bit field on the side to store the information, whether each of the value is null or not. And that's a simple way of capturing the null information. So the definition level is actually a generalization of that. Because when you have nested data structure, you have actually a path to this value, right? If it's A, and inside A you have a field B, inside B you have field C. And the definition level, we capture at which level in this path the value is null. So if it's defined, it's going to be 3, because it's valid all the way. If C is null, it's going to be 2. If B is null, it's going to be 1, and so on. So it's a generalization. Instead of our being 0 or 1, you have 0, 1, 2, 3 to know at which depth it is null. And the same thing for the repetition level. The repetition level would capture at which point in this depth, if you have nested lists, for example, it's going to capture at which point in this depth the field is repeated. And so if you want to understand more how it works, actually I published a blog post that explains this in details. But the one thing to remember is those two values, they're bound by the depths of the tree, right? So those are two tiny integers. They're not 0 or 1, but they're going to be 0, 1, or 2. And they're going to be small, and you know that in advance based on the schema, which means we can use bit packing to store them efficiently. So if for each value, we store those two extra repetition level and definition level, we actually can store them with very few bits. And it's going to be a very little overhead on the data, but that means that now we can store the data in flat columns, right? Because we have a column for this leaf. If you see the schema of the tree, each leaf of the tree is a primitive type, and we have one column for each of those primitive type in leaves of the schema. And we just store those values with a repetition level and definition level, and we can now reassemble them in those deeply nested data structures, and with very little overhead. Yeah, so that's a more detailed explanation of the repetition level, but just if you want to understand that better, I spent some time writing down the explanation, so please go check it out if you want to understand how that works. So there are several APIs. One, the main API is an API where you can iterate on fully assembled records, and that's the one we use for reading the data in Pig or in Scalding, and as you can read it also in many other frameworks. And at that point, you have this columnar data, and you want to be able to assemble the records and feed them in those row-oriented frameworks. And they both expose projection pushdown. So projection pushdown is the thing I was talking about, right? You need only a subset of the columns. So you need to tell the storage format, the storage layer, that you want to read only those columns. And so both Pig and Hive support automated projection pushdown, like Pig and Hive, because it's a query. They know which fields you're actually accessing through parsing your queries. And so they will automatically push down to the storage layer to tell it what columns need to be loaded. And for other things that are more opaque, like plain map reduce or Scalding or Cascading or Crunch, where you actually provide a function and there's no easy way to introspect it, then you have an API to select the field that you need. So a little more you just provide this information, and we lead on only those columns. And that way, you can have those faster scans and run your queries much faster. And it's, so Hadoop doesn't provide any notion of schema, right? But there are many things in the Hadoop ecosystem that provide a notion of schema, and they're all different. So Parquet, we spend quite a bit of time in designing an API that would be agnostic of all those things and integrate with all of them. The Parquet schema is pretty close to what protocol buffer does, because that's what Google does, which is very simple with very few primitives, but all you need to define a schema. And so we have mapping from Pig, Hive, Thrift, Avro, and protocol buffers to this schema, and you can read and write through all those abstractions. So you can take your protocol buffers, your Avro objects, Thrift objects, or your Pig tuples, and write them to Parquet and read back from Parquet. And also, like, integrate all those things, right? You can write with Pig, read with Hive, and so on. And so we have integration with Impala, Pig, Cascading, Avro, Spark, and Hive, and all those things. And you know, I didn't write all of those. I wrote initially the Pig and Thrift integration, and then looking at the APIs, looking at those as an example, different people in the community implemented all those integrations. So I'm going to skip on encodings because we're running a little bit out of time, but basically what I was saying, because it's columnar, we can also have much more efficient encodings. And one of the ideas of those more efficient encodings is that, you know, LZO or gzip, they're kind of general purpose, kind of trying to brute force compress things. But if we know more about the data, we can actually be smarter, right? If you know it's an int and you know the max value, you can do bit packing. If you know it's a field that is a string, you can build dictionaries and be much more efficient. It's much more efficient to look up a value in a dictionary than just having a byte array and trying to find redundancy in it. So Parquet 2.0 will have more encodings, things like delta encodings for ints and string. And this is already implemented, but need more testing. And we want to make sure it's also cross-compatible with the Impala implementation. Statistics that will enable predicate pushdown, which is doing more efficient filtering. So we have the projection pushdown that does better selection of columns, and filter pushdown, which is predicate pushdown, is more efficient filters using the statistics, because that way we can skip entire row groups if they don't. If you know no rows in there, will validate your filter. And also we're applying a new page format to facilitate skipping ahead at a more granular level. So I put a list of the main contributors, and I'm not going to mention them all, and you can look up on GitHub the contributor report, but we're happy that many people from various companies have been contributed and been interested in this, and a lot of systems are showing integration with Parquet. So if you have more questions, you can also, we have a mailing list, you can tweet at us, and please, you can come on GitHub and discuss and contribute. Thank you.